The next artifact is one that we introduced in our discussion of pulse repetition frequency and a quantity called the maximum unambiguous range, which is the maximum range within which a transmitted radar pulse can be scattered and received before the next pulse is transmitted. If a radar emits a pulse before the backscattered energy from the previous pulse is received, the backscattered energy will make it back to the radar, but the radar is unable to accurately tell which pulse it came from and how far the target is from the radar. This is called range folding, and it can have a significant impact on the readability of radar data. Thankfully, National Weather Service radars are equipped with methods to combat range folding, namely alternating between two different electromagnetic waveforms that each have different PRFs for the lowest few elevation angles. This almost always alleviates range folding in reflectivity data. However, radial velocity measurement relies on a single PRF, so range folding issues often plague velocity data. Range-folded pixels will appear as purple in most radar programs, indicating that the data cannot be recovered for those pixels. On the same token, every radar assumes that any returned echo is from the most recent pulse it emitted. If the radar receives backscattered energy from the pulse previous to the most recent, it thinks the return is from the latest pulse and, therefore, plots it closer than where it really is. These are called second-trip echoes, which manifest themselves as elongated streaks of echoes emanating outward from the radar along radials, where no active weather is occurring.
Chasing Dixie Alley is dangerous. We've got you covered. Free ebook link in description.
Precipitation particles scatter most of the electromagnetic energy from a radar beam in all directions, including back toward the radar. However, a fraction of that energy is absorbed by the particles themselves. This can cause the radar beam to become less intense the more particles it passes through as it extends outward from the dish, a phenomenon called attenuation. The amount of energy that's absorbed and, therefore, the amount of attenuation depends on the intensity of the precipitation and the wavelength of the pulse. If a radar beam passes through a light shower, the attenuation will likely be fairly minimal, but if it passes through, say, the heavy precipitation core of an intense supercell, the attenuation will be much greater, often erroneously decreasing the apparent intensity of more distant storms in line with the supercell's core. Also, shorter wavelength pulses are more susceptible to attenuation. This is why terminal Doppler weather radars and mobile radars are best suited for close-range weather observation. They use a shorter wavelength than National Weather Service radars and, in turn, suffer from greater attenuation issues. In this example from the TOKC terminal Doppler radar in Oklahoma City, located at the Pink Star, the beam was shooting through very heavy rain to the radar's immediate west. The storm farther to the west was of equal intensity to the band of heavy precipitation, but notice how reflectivity within the storm was significantly lower than that of the band. This is a product of attenuation as the beam traveled through the initial heavy rain band. Up to this point, we've described the radar beam as being focused within a single lobe of energy. However, this is not exactly the case, as radars have an imperfect radiation pattern. This creates weaker auxiliary lobes of energy that occur both in the horizontal and vertical, called side lobes, that can sometimes impact data quality, particularly in the velocity product.
Remember to check out those links in the description below, and then watch another video.